Morning, ladies and gentlemen. Now, my name is Rahul Banerjee, and I shall chair this keynote lecture, which will be delivered by Professor J.J. Vittal from National University of Singapore. While you guys are all settling in, let me say a few words about Professor J.J. Vittal. Professor J.J. Vittal has done his PhD from Indian Institute of Science, Bangalore in 1982. Then subsequently, he moved to NUS Singapore as a senior lecturer in 1997 and moved and became a professor very soon. So he's currently a professor at National University of Singapore. Professor J.J. Vittal has worked on many different fields in the solid-state chemistry, especially in the crystal engineering, and he is one of the leading researchers in the crystal engineering field. So in his work includes solid-state nanoscience, solid-state reactivity, reactivity within the solids, and also including the solid-state materials, creation of materials using the solid-state chemistry, especially the battery materials. This is something he has been trying in recently. And mostly some solid-state photochemistry using crystal engineering principles. A very simple objective of Professor J.J. Vittal's research is to understand and to utilize the principles of crystal engineering and try to understand the phenomena which appears due to those facts. So with this very brief introduction, I would request Professor J.J. Vittal to deliver his keynote talk, and I would also request all of you to give him a round of applause for that.
Good morning, everybody. Today I'm going to talk about some of the results from our laboratory. Before that, I would like to thank the organizing committee, especially Professor Desiraju, for giving me this stage to be here to talk about today's title. Of course, needless to say that I'm going to talk about the unusual. I put in a lot of this type of thing, unexpected, unusual, unpredictable, and all. It's my personal account. You see, some of the things that I'm going to talk about may be outdated, as you see. The next slide, I have, okay, sorry. The next slide, I've shown some of the solid-state properties, including physical and chemical. Some of them I have color-coded. Probably you see here, the first four, like the second harmonic generation, piezoelectricity, pyroelectricity, ferroelectricity, multiferroics, they're all associated with a particular type of crystals having non-centrosymmetry, lack of, centrosymmetry. And solubility, melting point and all, they're all common to all the compounds, but how you are going to control is another issue. As you see, crystal bending and movements are associated with a particular type of compounds. And as you see here, you may recognize that absorption, storage, and all associated with MOFs, including catalysis. I see that there are a lot of activities going on using organocatalysis. It's a very hot field, but I don't see anybody using organic compounds in the solid state to do catalysis. Anyway, conductivity and so on and so forth. Some of the chemical properties are listed here. I'm not going to talk about all these properties. I'm going to talk about a few of those things and why people are interested in all these properties of solids. Of course, they are related to some of the applications. So from application point of view, you want to make a better material. And in order to make a better material, you have to understand the crystal packing as well as intermolecular interactions. In other words, we are, as a scientist and researchers, we are interested in learning about structure-property relationship. Some people add function also, structure, property, and function relationship. And then, if you want to design, and then control, manipulate, and fine-tune some of the solid-state properties, where do we go? Crystal engineering. Crystal engineering will give you a lot of ideas and how to design, a solid that gives rise to a particular property. Okay, so we are interested in engineering the crystals to manipulate some of the properties. Are they predictable? Of course, see, as many people talked about it in the past few days, we need more and more data to get this one out. Whether it is predictable or not, it depends how much data we have to come into a conclusion. And as is, and also, once you want to design some solids, okay, that gives rise to the desired property. Then it goes to, the technology for applications. If it doesn't give, if it gives some unexpected results, then that goes to technological or knowledge advancements of knowledge. Okay, so today I'm going to talk about some of the things that didn't go the way we wanted. I have outlined some of the things, that I'm going to touch upon during my talk. Removal of solvents. We always, as a chemist, at times we have to dry the solvents, and also we grind them into powder for various reasons. And most of the time, we assume that nothing happens to these solids when you remove the solvents by drying in vacuum or heating it up to 100 degrees or so, and also grinding. You see, crystal structure does not vary. It retains its structure when you grind them. I'm going to show that it's not be the case in most of the crystals. And the other thing, the reason for us to do the reaction in solution is to make sure that the molecules collide, due to Brownian motion. During that, it will attain the transition state to get the desired product. So the mobility is important. As we know, the solid state, we don't want to do any reaction to solid state thinking that the molecules are rigid, they don't move. That's not be the case. Molecules can move, they can undergo, conformational changes. I have a couple of examples to highlight them. And also, you can indeed, modulate some of the reactions by putting a substitution. Fluorine substitution, nowadays it is gaining very importance in solid state chemistry. And few of the things I'm going to touch upon, I'll go to the next one is centrosymmetric crystals. As a crystallographer, we don't expect centrosymmetric crystals to show second harmonic generation. So I'm going to show, many examples, how this can happen. And the other thing, a normal crystallographer, a student will expect, a single crystal to be nicely well-defined with sharp edges and everything. And as you see, in our case, when we try to crystallize them, we started getting some curved single crystals. Finally, if you work in MOF, most of the time we don't care about the kind of solvents you have in the channel. You probably squeeze out most of the time. I'm going to show, what is in there in the channel is very important in some of the reactivity. That's what I'm going to touch upon, and some of the optical properties and so on and so forth. Okay, without further ado, let me go into some of the results. As I mentioned to you, the reactions do occur, when you try to dry a solid for various reasons. And this we observed about 20 years ago. When you remove water, associated with this solid, and it undergoes structural transformation. In fact, since then, at least 200 to 300, related work has appeared, how one can get the structural transformation by removing the solvents or adding a solvent. Actually, we reviewed this one a few years ago. This particular example I've shown is a simple linear coordination polymer. This is a silver coordination polymer. It has got BPE. This is 4-bipyridyl ethylene. We have an ethylene function here, olefin function here, and we have water that is bonded. We have acetonitrile. Naturally, when you have acetonitrile, it's low boiling solvent. When you just leave the single crystals, you would expect acetonitrile to go up. So what you get here will be, when you take the single crystals and leave it, it became powder. Then you would expect, okay, so acetonitrile is lost. Because of that, it loses crystallinity. In fact, during this process, the reaction occurs. Probably we would have missed this had we put in this olefin, functional group in this linear spatial ligand. Because of that, what happened, we know that in this crystal structure, this is the crystal structure of this compound, the olefin double bonds are not aligned. Okay, coming back to the origin of this 2+2 cycloaddition reactions, it was discussed on the day by Dario Braga, Hairu Moon, and one of the students of McGillivray, Shaliza, on Monday, so that gives me opportunity to skip some of the introduction on 2+2 cyclodation reaction. So you see here, because of the presence of olefin bonds, we know that they're all very far away to satisfy Gibbs criteria. Because of that, we know that this will be not photoreactive. On the other hand, the powder that we get was found to be photoreactive. The only way we can explain, for the photoreactivity of this compound is the movements of the coordination polymers. Of course, we had later, we have PXRD to support and other supporting evidences, and this compound was found to be photoreactive. Okay, so so whenever you you have loss of solvents, immediately you have to think that the compound need not be the same. Structurally, it may be completely different. And whenever we have solvents present in the crystal lattice, or the solvents that are bonded to the metals, the thermogrammetry experiments will give you a lot of information. In fact, you would expect a solvent that is present in the lattice will go away around the boiling point of the solvent. So water around 100. So if it is bonded to the metal ion, then it can go just above that temperature. For example, if water is bound to the metal, probably you may have to heat above 100 degrees, sometimes 150. But in this case, in this particular coordination polymer, we found out that you can remove the water that is bound to the metal ion below 100, around 100 degrees. Then, or below, it starts losing water around 70 degrees. Everything is completed by 100. Then we thought that will be a driving force for this exclusion of water that is present, that is bonded to the metal below its boiling point. Then we found out that when you remove the solvents, when you grind them into a powder and then heat them around 150, you get a powder. The powder was found to be photoreactive. On the other hand, the single crystals of this one, it's photoreactive if you irradiate for about 2-3 days, and probably due to deterioration of the crystallinity and everything. So we found out that the dehydrated sample was found to be photoreactive. And we can explain using intermolecular interactions how the removal of water can promote the formation of new bond from the nearby carboxylate oxygen atoms. So we can explain the reactivity very easily using intermolecular interactions that are present in this compound. This is another example. Now, usually, again, coming back to grinding, whenever you try to grind a crystal into a powder, again, we think that nothing happens to it. And also, when you have a solvent, what do? Either you want to remove the solvent first, or grind them later, or grind them first and then remove the solvent later. How does it make this? What difference do you expect? It doesn't matter how you do it, right? And I'm going to show you it makes a difference in this particular case. This is a one-dimensional coordination polymer. In this one, you see it has got a DMF molecule bonded to copper. And if you take a look at the thermogrammetry of this particular compound, you see that it started losing DMF just below its boiling point. Actually, you can remove it by 140, where the boiling point of DMF is 153. That says that something else is happening, that is driving the whole DMF from the metal, out of this one at such a lower temperature. But when you looked at this crystal structure packing, it doesn't say anything much. Okay. Then we thought, okay, we want to investigate the photoreactivity, having the functionality, the olefin bonds here. We want to take a look at it and see what are the what kind of information we can get it. So this is the NMR spectrum of the compound with DMF, and then you can remove the DMF. In this case, either you can grind them first, desolvate, or desolvate first, grind them. It doesn't matter. You can remove it. But if you take the crystal that is desolvated under, desolvated first and then exposed to UV light, you see the reactivity. We have got some unreacted, one-dimensional polymer here, and most of the double olefin bonds have been consumed, and about 80% of the reaction occurs here. On the other hand, if you grind the crystals first and then desolvate them, it undergoes 100% 2+2 cyclodation reaction. We were wondering what is really happening. Let me recap. The ground and desolvated samples to 100% conversion, whereas desolvated single crystals, you don't touch the single crystal but just heated them, it undergoes 80% conversion. You see some of the work, theoretical work that have been done in the past, including Kannan and Desiraju, in 1986. They say that if the double bonds are aligned in an infinite array, in parallel, you would expect around 82 to 87% conversion. That's what you would expect if it is a 2D, sheet. It's a sheet-like structure as shown in here. Okay, that's what is happening. That's why you are getting about 80% conversion. So you can say that just by desolvating the crystal, this 1D polymer goes to a sheet-like structure. And then what is interesting is, if you take this compound, if you grind them, after you grind them, you do 2+2 cyclodistant reaction, it goes to completion. So the only way we can explain is, it goes to, the sheet structure goes to ladder-like polymer, because ladder-like polymer, you have got the alignment, intact, and then, it satisfies the Schmidt criteria, so it undergoes 100% photoconversion. On the other hand, if you take this compound, you grind them first, and then remove the solvent. Directly it goes to ladder-like polymer. So from this, we find out that a simple grinding can change the dimensionality of the coordination polymer in this particular case. Okay, in this particular one, in the slide, I had shown the packing of this pyridyl acrylic acid. This particular, compound was extensively used by various people. Actually, Dario Braga, in his lecture, he also talked about it. And so this is the salt made by trifluoroacetate, and the double bonds are nicely aligned in a head-to-tail manner that undergoes 100% 2+2 cyclodistant reaction. If you take the simulated powder pattern and then the powder it and then take the PXRD of the bulk, it exactly matches. And the same thing happens if you follow the course of the photoreactivity. If you grind them into a powder, it goes faster a little bit because more surface area are exposed to UV light. So you would expect the reaction to be slightly faster than the single crystals. So how about the other compound? So when we change to sulfate, okay, this forms sulfate and bisulfate. It has got water, and this is the packing. In this packing, you have all head-to-head, alignment of the double bonds here. And also, all the double bonds are nicely aligned within, satisfying Schmidt criteria in terms of distance, but some of them are aligned in anti-parallel way. So usually, the anti-parallel orientation of the olefin ligands will not be reactive. If it is reactive, it has to undergo petal-like motion. But in this case, when we take the single crystals and follow the course of the reaction, we got close to 60% conversion. That as expected, because in this case, the anti-parallel alignment of double bonds did not participate in 2+2 cyclodistant reaction. On the other hand, if you grind them into a powder, it goes to 100%, and in a very short period of time, in 60 hours. So we were wondering, what is really happening? You can immediately, come to a conclusion that there will be a phase change. Of course, there will be a phase change. If you see, the simulated, PXRD pattern is completely different from the powder pattern obtained from the bulk, after you powder them. But when you do the thermogrammetry of the ground powder, you see that it takes an extra water molecules from the humid air, and the composition has completely changed. So that is surprising. When you have single crystals, it has got one composition. When you grind them into a powder, it has got completely a different composition. Because of that, you would expect 100% photoreactivity in the case of powder. This is another interesting to us, at least at the time. When you try to, after that, we were very careful. Whenever we try to follow the course of the reaction using 2+2 cyclodistant reaction, First, we will do it with single crystals and then do it with powder and then make sure that what's going on. In many cases, it gave very interesting results. One can also, do some in this case, what happened when we are trying to make pellets for, to record IR, we found out that some of the coordination polymers, they react with KBr on grinding, especially when you have acetate and trifluoroacetate, you need to be careful. You better use Nujol, don't grind them, with KBr. Previously, I've shown that you can very easily remove the solvents that are present in the lattice or bonded to the metal at very low temperature. In this case, it's the other way. This particular metal complex, okay, as shown in here, these are all lanthanum, praseodymium, and samarium. It has got two diethyl ether trapped into it. They're strongly hydrogen bonded. Okay. When we try to do the thermogrammetry of the compound, surprisingly, the lanthanum compound can, can lose diethyl ether at around 82 degrees. That's well above the boiling point of diethyl ether. On the other hand, if you change the metal to to praseodymium, then it's 69, and when it's samarium, it's about 50 degrees. So, which is quite interesting because a simple metal complex is able to retain highly volatile diethyl ether. Then one would think that, okay, probably this diethyl ether is trapped inside the crystal. That may be the reason why it is not able to come out around its boiling point. When you look at the packing structure of this, there's a channel going through. Actually, you have diethyl ether that can easily be removed. So you're wondering, even such a small, with such a weak, in terms of, in organic crystal engineering, hydrogen bond being very strong, okay, even the hydrogen bond between the water and the diethyl ether is able to retain diethyl ether well above its boiling point. Of course, we have done some TGIR and TG-MOS spec to show that's what is happening. You can see a direct correlation between the temperature of diethyl ether release in this case. We should be able to control the retention of diethyl ether in these simple metal complexes. Okay, here I've shown the crystal structure, actually the packing of a simple metal complex. This is the work of Pirikakal Abdul, who is here among the audience. It was done some time ago. As you see here, this is a metal complex. They are nicely complementarily hydrogen bonded, forming one-dimensional tape-like structure. If you analyze the packing very carefully, you will see that this is 2/3. Actually, yeah, 1/3 of them have parallel alignment. 2/3 of them have anti-parallel alignment. If you have something like that, when you do the photoreaction, you would expect this anti-parallel olefin bonds will undergo some kind of pedal-like motion, and then it will become parallel, then you will get 100% photoreaction. And that's not be the case, as you see here. If you have the single crystal, and then if you do the photoreactivity, the anti-parallel aligned olefin pairs are not, going through the pedal motion, and you get less reactivity. On the other hand, if you grind them into a powder and then expose it to UV light for about 25 hours, and then you will see 100% of photoreactivity. Okay, 100%. And as you see in this particular compound, let me go back, you have some bipyridyl ethylene molecule bonded to the metal, and you have 1/4 of BPE in the lattice. I'm going to show the solvent, the guest molecule, guest BPE in the structure soon. But as you see here, in addition to it, if you analyze the proton NMR spectrum, you would see that about 87% of them are due to RCTT isomer. This is what normally you expect in 2+2 cycloaddition reaction, because you want them to be parallel and closely within the distance of 4.2 angstroms. On the other hand, we also got 12.5% of this RCTT isomer. So that it says that the BPE in the lattice is also participating in the reaction. If you analyze the crystal structure of the other layer that contains nitrate, water, and BPE, I mean, they're all very, there's no disorder. You can in fact, refine the hydrogen bonds, hydrogen atoms, and then you can clearly shows, that they are nicely hydrogen bonded. And the distance between the BPE molecules are more than 7 angstroms. But, when you grind them, you see 100% reactivity. And we reckon that, the 25% of the reactivity reaction comes from this BPE that is present in the lattice. Then we, since we observed 100% reactivity, we came to a conclusion that, this BPE molecule swam across, in the pool of water and nitrate. And then when they come closer, you have got 2 different orientations. Either it can be parallel or anti-parallel. That gives rise to 12.5%, RCTT and 12.5% RTCT. So, I mean, now we know that we are just surprised to find out at the time that this kind of molecules in the lattice can move more than few angstroms like this. Okay, when we were investigating, this is another example from 2+2 cycloaddition reaction. This is a simple metal complex, a dinuclear metal complex with zinc. Sorry. If you take a look at the packing of this particular compound, you will see that on one side, the double bonds are nicely aligned to undergo 2+2 cycloaddition reaction. On the other side, actually, it's slightly disoriented. In fact, if you just take a look at the position of the methyl group on the benzoate, you see that this is hindering the movements of this. From here, the CH3 is present, so it cannot come closer. Okay, that prevents the 2+2 cycloaddition reaction in this particular compound. So when you take the single crystals, it undergoes only 50%, forming a dimer. And if you take a look at the crystal structure of the dimer, still, that particular methyl group is locking, okay? And that prevents any further reaction in the solid state, in the single crystal state. On the other hand, if after the 2+2 cycloaddition reaction, you take those single crystals and powder them, and those powder undergoes 100%. And then when you compare the PXRD, you see the phase change immediately. So when you grind them, yes, of course, they undergo phase change. Because of that, the double bonds are aligned in the powdered state, and hence we get 100% photodimerization. When we change the substitution on 4-stearyl pyridine, excuse me, it's exactly the same. Okay, this is isomorphous and isostructural to the previous compound with 4-stearyl pyridine. This is also a dimer. Only thing is you have extra fluorine that is bonded to it. Again, on one side of it, you have parallel orientation of the olefin bonds. On the other hand, on the other side, it is slightly slip-stacked. And you see this, the double bond from the fluorophenyl group is closely aligned to the double bonds of the olefin here. Whenever you have something like this, okay, we would expect this one to undergo 2+2 cycloaddition reaction smoothly. On this side, you would expect no reaction. That's what we found out in the case of 4-stearyl pyridine. But to our surprise, on both sides, this reaction occurs. Interestingly, we got something different. In this case, the olefin bond reacts with the aromatic, this phenyl group, forming a new type of, this is quite surprising reaction. And we were able to characterize not only the solid state, but also using fluorine NMR and proton NMR spectra and all. So we thought this is quite unusual for a fluid, the olefin bond reacts with the phenyl double bond here, forming this type of compound. So what we think it is, as a crystal engineer, we can bring the double bonds, olefin bonds, very closer, to satisfy Schmidt's criteria using different strategies. Okay, so you can bring them very closely. What happened? After you bring them closely, they will undergo either pedal motion or sliding to form this cyclobutane derivative. This is like normal behavior. You can bring horses to the pond, leave it, it will drink water, right? In the case of fluorine substituents, what happened? It's not normal. There's no sliding in this case. In the case of 4-chiral pyridine, in the single crystals, but here it undergoes unusual photodimerization that has it's very rare. That has not been observed in the solid state. Not many anyway. We thought this is very unusual behavior. Okay, like a horse drinking orange juice. Okay, this won't happen. Maybe this happens once in blue moon. But in this case, probably it's wearing the glass that is fluoro substitution here. This occurs. I'd like to see more of this type of 2+2 reactions between olefin and phenyl double bonds in the future. But come to if you analyze the literature, you will find out that this intramolecular cyclization between phenyl and olefin groups are very well known in solution chemistry. Every day people are using but intramolecular is very unusual. I've seen only one report before. Okay. When see, I just now mentioned that these type of compounds can undergo 2+2 cyclodation reaction. We thought, why don't we change toluene by benzene? It should behave quite similar to what I described before, but it's completely different. When you have zinc benzoate, and when you take a look at the packing of this, it's beautifully aligned to undergo 2+2 cyclodation reaction. But at the same time, they also pop like popcorns. If you put the popcorn into hot container, it starts popping. So that's what happened in the case of this particular compound. Okay, we thought this is quite unusual. We have done this work with the help of Ponzanamo, who's sitting in the audience. I'm going to talk about the compound that we used here, that shows photosalient behavior. Okay, I'm going to change the gear of my talk a little bit. I'm not sure how many of you are familiar with this particular photograph, and probably if you're working in late 70s and 80s, probably you can recognize he is Dick Marsh. If you see, usually as a scientist, we want our papers to be cited, okay, many times, okay, but you don't want our paper to appear in his cited by him. Okay, if he is citing your paper, that means something wrong with your crystal structure. Most of the time, it'll be centrosymmetric space groups versus non-centrosymmetric space groups. Okay, so as a crystallographer, we have been trained, to choose centrosymmetric space groups over non-centrosymmetric space groups. There are a lot of reasons for that. In the absence of any experimental evidences, as I mentioned to you, he published several papers on this. Nowadays, things have changed because there are various ways to prove whether a crystal is centrosymmetric or non-centrosymmetric. Things like FLAC parameters and other things can be used for this purpose. Okay, coming back to this particular compound, it crystallized in C2/C. My student at the time, after we published the paper on photosalient properties, he came to me, one day and said that, sir, this, this shows second harmonic generation. I was really surprised. Are you sure this is the compound? how did you crystallize? I asked so many questions, and finally, we found out that this is the compound that is showing second harmonic generation. And we have done, he has done a lot of experiments with the help of Nalla Venkatram from NTU. And then he showed that, and not only that, the intensity of SSG is twice that of KDP. We always compare, whether we have done anything wrong. And also SSG is maximum at minus 50 degree Kelvin. So interestingly, when you have forced-sterile pyridine, that shows, this non-SSG. When you replace this one by fluorine, all these compounds are isotypical, but these two do not show any SSG properties, only the sterile pyridine. So we thought, okay, the experiment is correctly done. We are dealing with the right compound. We were wondering, at the time, we didn't have much to offer in terms of, why this is happening. We say that, okay, this is, in this particular case, we got a polarity excess of one type of handedness crystallized in this compound. That could be the reason why this is happening. When we try to, when we try to do the refinement in CC, again, FLAC parameter was very close to 0.5, maybe, sometimes, 0.6 or 0.55, 0.75. But the thermal parameters, were not really very good. But this is an experimental evidence, okay, that we know that this particular compound shows SSG. Because of that, it has to be non-centrosymmetric. Recently, I looked into some of the literature on this type of compounds. See, the one that is published in 1990, they have taken R-N-acetyl valine and then N-acetyl valine. They recrystallized it from methanol, and they took a single crystal. The single crystal shows SSG. That is crystallized in P21 upon C. Again, I looked at their explanation, which is not quite satisfactory. But when you see the work of Desiraju, Curtin, and Paul, they have co-crystallized quinone and hydroquinone derivatives. In 1979, they found out that these crystallized in P21 upon C, and they explained this one may be due to, this is not the right space group. They said it is due to random distribution of P21 and PC. Probably, in our case, C2 upon C, we have, it may contain some random distribution of CC and C2. When you have the mixture of those things, that's what you expect, we thought there should be more explanation to that. In fact, on Monday, Braga gave a nice talk on, which he just touched upon this particular aspect. But we thought there's one more way to explain. Again, I'm ready to take any criticism of this proposal. See, when you have a centrosymmetric crystal, you see the center of inversion. And these two are chiral crystals. This is, enantiomorphs, two enantiomorphs. But in the case of non-centrosymmetry, you have the mirror. You can also have glide, of course. When the crystals of opposite polarity, when they pack them something like this, you do have some one type of polarity and opposite type of polarity in one single crystals. But if you in the single crystal, the X-ray cannot see the presence of this the racemic the mixture that is present in the single crystal, because it's averaging all the time. So what you see is centrosymmetric. That's the reason why probably we missed it. There should be another explanation. I had given 3 different explanations so far for the observation of SSG in centrosymmetric crystals. Usually, our single, when you try to grow crystals, it'll, as I mentioned to you, it'll have straight edges and sharp edges and straight faces and everything. And in many cases, you can also get curved crystals. in the case of nanocrystals, especially in nanochemistry, you should be able to control the kinetics, and hence you can get different shapes of single crystals. And we have got many of these things we published several years ago. When you have a single crystal, you should be able to bend them also, elastically, elastic bending as well as irreversible bending. We have seen many talks, and many stalwarts are here on mechanical bending. But when you try to crystallize them, usually, you get normal single crystals. But recently, Bodkar published a review in Angewandte, that was in 2014 or 15, and he compiled, all the curved crystals. Indeed, you can, if you take, for example, potassium dichromate, if you crystallize them, you can get really beautiful curved crystals. So, but, for the first time, in coordination, a simple metal complex, when you try to crystallize them, you get beautiful curved crystals. We thought this is something interesting. We first want to find out, is it crystalline? Yes, it is crystalline. You can cut the portion of these curves, and then you determine the crystal structure. They're perfect. It's not polymorphic. It's not polymorph forms and everything. It's exactly the same as the other one, normal one. And we try to explain why this is happening. If you take the look at the crystal structure, the packing of this particular metal complex, where you have, this is 3F 4-shell pyridine, and then this is zinc, and this is tetrahedral coordination, and you have 2 isothiocyanate bonded to it. This is the packing of this, and on 4 sides you have DMF and water. So it is completely immersed in a pool of DMF and water. And how do we explain the curved nature? We try to gather some experimental evidence. I don't know how to do it. That shows our inability. So, but anyway, we try to explain it, because when you try to pack them in one of several hundreds of those metal complexes, probably you change the coordination number, because you have DMF and water. They're all highly coordinating close to it. Probably one of the zinc atom goes to coordination number 5. That will tilt the whole thing. So this is happening periodically because of the presence of 5 coordinated zinc. In 1 in few hundred, of these molecules, they started tilting like this. It's again highly qualitative. And now we got, few other crystals that shows the similar behavior. Probably we'll try to gather more experimental evidences to prove or to show what is really happening. Currently, we don't have much experimental evidences to show them. Here, this slide shows, what happens if you change the substitution. Even for the same 3F, I've shown that, if you try to crystallize from DMF water, you start getting the curved crystals. If you change the solvent to methanol, you get a normal crystal, photoreactive crystals that undergoes 2+2 cyclodation reaction due to the presence of this, the olefin bonds here. When you change to 2F, then that shows photosalient behavior. Okay, let me switch, the gear of my talk a little bit. This is on photopolymerization reactions. We recently started working with the ligand BPEB that contains 2 conjugated double bonds in the structure. We have a phenyl ring in the middle. It's the way you arrange them. It can be face-to-face dimerization or single 2+2 photoreaction. But if you correctly align them, in a slip-stacked manner, this can undergo 2+2 cyclodation reaction that will lead to the formation of polymer. Okay. And also we found out that this particular, during that, this is what happened when you have this morph that contains this particular ligand with BDC. That forms diamondoid type of framework structures. And then when you try to put it in UV light to, for the double bonds to undergo 2+2 cyclodation reactions, you get a polymer that is embedded inside the morph, 3-dimensional structures. Actually, this was a 6-fold interpenetrated structure that goes to non-interpenetrated compound that contains a polymer embedded very nicely. So it is a hybrid of both one-dimensional, 1D coordination polymer and then real organic polymer inside the crystal. We found out that, here the conformation of the BPEB is trans, that led to one particular type of tactic polymer, is isotactic polymer. Okay, so we also found out a similar alignment in other compounds also, the slip-stacked arrangements of BPEB that gave rise to the organic polymer embedded inside the metal organic framework structures. The interesting thing is not that, that's not unusual anymore. A few years ago, we tried to synthesize this pillar layer compound. In that we find, when we use BPEB ligand, you can change the conformation, okay, in a single crystal to single crystal manner. In this particular compound, this is threefold interpenetrated compound, PCU unit shown in here. In this particular one, it has got trans-cis-trans conformation. The single crystals, if you put it in, that has got DMF in there. If you soak it in methanol, it goes to another form, and the conformation changes to trans. Okay. In this particular compound, the double bonds are not closely aligned. It's found to be photo inactive. My graduate student, at the time he was in Korea, Korean student, Dr. Inya Park, and he took it because I just now described about the conformational changes, single crystal to single crystal manner in methanol and DMF. He took this compound and just heated them up to very high temperature to get rid of the solvents. So what happened in this case? It loses the solvents in the channel, and when you cool it, it takes water back from the air. Okay. So these two we have found that to be photo inactive, but this compound, he found them to be photoreactive. In fact, there's not much difference between these two. Previously, when we published this paper, we didn't pay much attention to the solvent that is present in the channel because it's highly disordered. We just modeled it to disordered water and we published. We thought it's, who is going to care about what is present in the channel? So at the time, we published this as water. But, you cannot have these two because, this is one MOF with water. When you heat it up, cool it down, it takes back water. This is photo, inactive, and this is photoreactive. How do you explain? And the photoreactivity also gave rise to a different type of isotactic polymer. I'll give you some more details of it. So these are the crystal structures of the compound before and after. Okay, so you can see the formation of polymer in the crystal that gave rise to different type of tactic polymer. Coming back to those crystals, I'm just comparing the compound, the crystal that is photostable, the other one that is photoreactive. Exactly, the crystal data is more or less match. And if you take a look at the distance between the olefin bonds, they are more than 4.8. You can expect them to be photoinactive. This is what happens in the case of compound 2. The superimposition of these two, the repeating units, they're perfectly matching. There's no difference. As I mentioned, the only difference is the solvent that is present in the channel. In the photoreactive crystal, it is water. We know that. The previous one, later we went back and analyzed, using TG mass spec and IR, NMR, and everything. We showed that it contains water and methanol. So in this case, it contains water. Why do we expect two different reactivity? And how do you explain it in the first place? Okay, I just mentioned that the conformation of the BPEB is trans. From the type of product that we got, okay, that is a tactic polymer, that could only be obtained if you have trans-cis-trans conformation. So that means, the intermediate of this reaction is trans-cis-trans. So when you shine light, it undergoes petal-like motion. that is known in the literature. So it goes to cis-trans conformation, and because of the change in conformation, brought these olefin bonds closer together. Now it is reactive due to pedal motion. Okay, fine, you can explain it. But why this is not, I mean, if you can explain this, you should be able to explain this one also. You would expect this one also to be photoreactive, but not, but this is not. How do you explain it? The only difference is methanol. We know that, by changing the solvent, you can change the photoluminescent properties. That's what we use it for sensing, the MOFs. Okay, if you change the solvent, the physical properties changes. This is the first time we know the presence of methanol prevents the pedal motion of the double bonds. Okay, this is something we learned. Otherwise, we cannot explain this observation. Okay, as I mentioned, we can create two different type of tactic polymers. In the previous case, with diamond type of network structures, we were able to, produce isotactic polymer embedded inside the MOF. In the other one, we can get syndiotactic polymer that is there. Okay, I think I still have a few more minutes to touch upon some of the recent results. When we have fair success with BPEB ligand, we want to be smarter. Actually, we want to just extend our work to include 4+4 photocycloaddition reaction by replacing the phenyl ring by anthracene. Okay, if you have something like that, okay, this is the ligand design, we thought, okay, so this can undergo 2+2 on both sides. If these two fails, and this will undergo 4+4 cycloaddition reaction. So we want to do, multifunctionality into it, depending upon the radiation, the wavelength that you use. We found out that this is photostable. You cannot dimerize them, even if you align them very close to it. We found out later that, this particular ligand is very interesting, and it has got, this is, acceptor, donor, acceptor type of things, and we have double bonds in the middle. And also we found out to be diradical, singlet diradical at room temperature. Yes, it shows ESR. And also if you dissolve them and measure ESR signal, that vanishes. So that is present only in the solid state. Okay, so we made this MOF. I'm going to talk about the MOF that shows quite interesting properties. Before that, I want to introduce some of the emission process that can occur in the solid state. This one we are all familiar, CARS, coherent anti-Stokes Raman scattering. Okay, this goes through a virtual state, and then it emits. The second harmonic generation, again, involves virtual state, frequency doubling, exact doubling. Okay, THG is third harmonic generation. Again, you triple, the frequency tripled here. Again, this involves virtual state. As in the case of two-photon excited fluorescence, this involves, this is a real excited state, and it's not exactly double or triple. It's slightly less than that due to vibronic relaxations. Okay, so but still, it's not just 2-photon. You can also have 3-photon, 4-photon. There's a recent paper that deals with 5-photon excited fluorescence. Okay. In addition to it, we have lanthanide subconversions. I'm not going to touch upon those two. Coming back to our compound, that that is a pillar layer compound, that shows 2-photon, 3-photon, 4-photon emission, beautifully, and we try to explain it. That's because of the presence of the ligand. Let me go back. That's due to the presence of this particular ligand. You see that the emission of the ligand as well as the MOF are more or less the same. So the emission of the MOF is highly dominated by the presence of this particular ligand. So coming back to it, and also this involves faster resonance energy transfer. I don't want to go into the details of it, but you can increase the quantum efficiency of this particular multiphoton harvesting property is about 17%. You can increase it by incorporating perylene and anthracene into it, so up to 28%. The same compound shows third harmonic generation. Usually, if you take any compound, if you test it, they will show third harmonic generation. It depends on the intensity, that'll be, that's useful for various applications. But the same compound also shows third harmonic generation. And recently, we made a series of those MOFs, and then we show that the physical chemical properties can be fine-tuned, and as well as the quantum efficiency. Okay, this is an interesting part of these optical studies. We made this ladder structure that has the same ligand, which I mentioned. We also have benzoates, as a bridging ligand, as well as chelating ligand. The structure is shown here. This particular compound shows third harmonic generation. As I mentioned to you, it's very strong, okay? And also it shows 2-photon, 3-photon, and 4-photon, emission. In addition to it, it shows second harmonic generation, all in one. The same crystal shows all these properties. But take a look at the symmetry. It's centrosymmetric, P1 bar. Again, we have problem of explaining. Okay, I mean, again, can we go back? And we were wondering, how to explain this phenomenon. But there are a lot of literature to support. I'm going to show in the next slide. We introduced, we explained by introducing local defects. In this one-dimensional ladder structure, you can have missing ligands, missing bridging ligands, or, so those things can give rise to this type of defects that will give rise to non-centrosymmetry. Okay, there are a lot of papers that appeared here. Yagi since 2011 started publishing, and there is a review that appeared here by Roland Fisher. He reviewed the defects in MOFs. In fact, the defects in MOFs, people are using it for applications like catalysis and absorption. This is the first time we found out that these defects can also create non-centrosymmetry. Okay, I'd like to summarize my talk by saying that, most of the time we just assume a lot of things and then go ahead and do, and then we found out that some of them are quite different from what we would expect. But if you, look at the reason for those things, we'll find out that we still need to learn more than what we know already anyway. Still, so with that, let me go back to acknowledging some of the students that are involved in this project. It's not in this particular project, and I'd also like to thank Professor Lee and a few of my collaborators, including Panzanamo, and Mir and Abdul are also here in this audience. I'd like to take this opportunity, 2 minutes, to advertise our ASCA meeting. That's in Singapore in 2019. If you have visited Singapore, I'm sure you would like to come to Singapore again. If you haven't seen Singapore, it's an opportunity for you. And this time we are going to have it in the university itself, so you'll have a taste of living in NUS and going around this campus. I'm sure you will love it, and please mark in your calendar. And I have left a few announcement, the flyers up there. Can you pick it up and while you're leaving this room? Thank you very much.
Thank you very much. Thank you for full presentations. We have time for a couple of questions.
Thank you for this presentation. It was very interesting. However, I have a comment and a question. First thing is that second harmonic generation cannot be observed in centrosymmetric structures. This is just basic algebra of tensors. Because when we have second order effects, we have that represented by polar third rank tensor, which is susceptibility tensor in this case. When we have center of symmetry, then all the tensor components disappear. So you showed a quite nice scheme of the second harmonic generation with a single crystal showed in the picture. However, you measured for powders. When you measured powders relative to KDP, how did you check the purity of your sample? Because grinding of the sample, which happens when you perform SHGS experiment, can cause phase transitions. So you can have multiple phases in there. You can have a non-central symmetric phase. A second possibility of your effect can be related to heating of the sample and the phase transition upon irradiation with the laser. There are not all the options. It is impossible to have this effect.
That's true. Actually speaking, the one that shows SSG, if you powder it, the SSG vanishes. And recently we found out that a few more crystals, if you replace zinc by copper, they also show SSG, actually a few more. So this is an experimental fact. This is an experimental observation. How do you explain it? Still it's open in the air.
You have to be sure that you have exactly pure phase, I guess, in this case. And maybe DSC can also be used to check if in high temperatures you don't have a phase transition, because in other cases it's impossible. Thank you.
It's not very often that I hear a description of my PhD work in a scientific conference. But talking about the old example of phenyl quinhydrone, and since this is a crystallography meeting, I'd just like to suggest to the audience that there are limits to the X-ray method. And in that phenyl quinhydrone, I remember it ended up with an R factor of 10 or something and just got stuck there. It's one of those unsolved structures. Also a message to young PhD students in the audience. It's very nice to have a PhD problem where you don't get to the answer in the end and it remains unsolved. And I don't believe the problem of phenyl quinhydrone has still been satisfactorily resolved. There are two domains of PC and P21, and the X-ray result just shows P21 by C. It showed a SHG very clear, and of course that shows that there are P21 domains. But I would really suggest that in addition to X-ray diffraction, we have other things like SHG, solid state NMR, so many other things, terahertz, and one should try to use a whole basket of techniques in order to get to the finer structural details. And some of these compounds which do not respond easily to single crystal X-ray diffraction, they might contain the most interesting problems. So as I reach the end of my research career, I'm almost tempted to go back to phenyl quinhydrone and start looking at it again. Thanks a lot, JJ, for mentioning it.
Okay, we shall take one last question. Yes, please.
Okay, thank you very much for a fantastic talk. I'm more interested about the photo-inactive and photoactive scaffold that you showed there. Is there a possibility that the methanol that is trapped in the channel acts as a spacer between your scaffold, that it inhibits much more hydrogen bonding to happen between your scaffolds? As I saw that the distance between your scaffolds is like 4 point something, but then in a case where you have only water, you got the scaffold to be photoreactive. It's proven much in literature that solvento gas molecules in solid state studies, in terms of photoluminescence, they have huge effect in their luminescence. Is there a chance that maybe that is the case, that the methanol is acting as a spacer in your channels?
No, I don't have, so no. I don't think we have, any changes in the photoluminescence.
I'm sorry?
I don't think we have any change in luminescence between water, methanol, and water compound.
No, actually, I'm talking about the methanol thing. Like why we have photo-inactive and photoactive.
Yeah, but still, we don't know. This is what we propose. This is the experimental fact. In the case of water, it undergoes, kind of pedal-like motion that brought the double bonds closer together. In the case of, methanol containing MOF, it doesn't occur. We don't know. These are the things, this is the first, maybe the first example in this. We need to investigate more to understand what's really going on.
Okay.
Actually, we are doing some more. In fact, you can take methanol and put it in water, the water containing one, or various other solvents, and look at the photoreactivity.
Okay. Just for a comment, in photoluminescence studies, what I've seen in the literature now, they are heavily looking into the solvento interactions with the prime molecules and how the interaction mode between the prime scaffold and the solvent and how it influences the whole photoluminescence thing.
Yeah,
maybe
but
you can look in that direction.
Yeah, but in this case, they're all disordered, highly disordered. Okay. We got this information only from NMR, TG, mass spec, and IR and everything. So if you know how the hydrogen bonding, if there is no disorder, then we can look for hydrogen bonding. Then we'll learn more about, we'll get more insight into this type of problems. So far, we don't have.
Okay, in the interest of time, we have to close this session. I'm sure you have many questions, but you can take it up during the tea break. Please join me thanking JJ for this wonderful presentation. We have Kumar Birada for a small...
On behalf of LOC, this is my great pleasure to give him a small gift.
Thank you.